Every textbook shows you recursive functions that are already beautiful. Nobody writes them that way. In this video, we build a recursive membership test the way a programmer actually does. We write a version that is wrong, watch it fail, hunt the bug with a print statement, fix it, and only then clean it up. Along the way, we meet a rule that makes recursion click. Every return statement must hand back the same type. Here is a new list problem. Instead of summing the elements, we ask whether a particular element is in the list at all. The function in list takes two arguments, the list L and the element E we are searching for. Follow the same pattern as the sum. Base case, a list of length 1. With only one element, that element either is the one we want or it is not. So we return the Boolean, whether the first element of L is equal to E. Notice this hands back true or false, not a number. Now the recursive step, and here is the tempting thought. If the list is longer, just look for E in the remainder. So we call the very function we are writing on everything except the first element, still searching for E. It looks exactly like the sum function looked, but this version is marked incorrect, and we're about to see why. Time to test it. Take the list 2, 5, 8, 1 and search for 0. The function returns. False, 0 is not in the list, so that is the right answer. Search the same list for 1 and it returns true. 1 is in the list. Found it. So far, the function looks healthy. Now change the input only slightly. The list 2, 1, 5, 8, searching for 1. The element is sitting right there in the second position. Run it, and the function returns false. That is not okay. Same four numbers, same element, just a different order, and the answer flipped from correct to wrong. Something in this function depends on where the element sits, and that should never be true of a membership test. When recursion hands you a wrong value, the fastest diagnostic is a print statement inside the function itself. At the top of InList, print the list we are currently examining and the element we are looking for, then run the failing case again. The trace reads, looking for 1 in the list 2, 1, 5, 8, then looking for 1 in 1, 5, 8, then in 5, 8, and the last call, looking for 1 in the list holding just 8. There is the disease. As the calls walk down these shrinking lists, they skip right past the element we want. The slice drops the first element every time, but nothing ever compares it to E. The only comparison in the whole function happens at length 1. So this code answers a different question. Is the last element the one you are looking for? Notice it can never claim to find something that is not there. Its only failure mode is missing something that is. The recursive call itself is fine. Searching the remainder of the list is exactly right, but only in one situation. When the element we just dropped is not the one we want. So give the else branch its missing check. With more than one element, extract the first element and compare it to E. If it is equal, return true immediately. There is no reason to search the rest of the list. If it is not, then recurse on the remaining elements with the exact same function. Run the test again. 2, 5, 8, 1 searching for 1. True. And the case that broke us. 2, 1, 5, 8 searching for 1 now returns true as well. The function is now correct on every non-empty list because every element gets its comparison before it is dropped. Nothing here is tied to the front of the list. A symmetric version checks the last element instead, and it recurses on everything except the last. Right to left, same correct answers. What matters is the principle, not the direction. Here is an honest confession from Dr. Bell. The beautiful, cleaned up recursive functions you see in textbooks are not how anyone thinks about the problem. She could never have produced that polished form on the first try. Her actual method: separate the problem into cases. Work out the case where the list has one element, then work out the case where it has many. Solve each one on its own and do the cleanup afterwards. Watch that cleanup here. The same comparison, the first element of L against E, is written in two places, so they fuse into one branch. That opens up a new, simpler base case. If the length of the list is 0, the element is certainly not there, return false. Then if the first element is equal to E, return true. Otherwise, recurse on the rest. 3 branches and it reads cleanly. Test it. The list 2, 5, 8, 1, searching for 1, true. The list 1, 2, 5, 8, searching for 1, true. And the list 2, 5, 8, which does not contain the number 1, false. One caution before you fall in love with cases. Do not hardcode a ladder of base cases. Length 0 does this, length 1 does this, length 2 does this. A few reasonable base cases are fine. The recursion should handle the rest. One more rule, and Dr. Bell says nobody made it clear to her when she learned recursion. Every return statement in a recursive function must hand back the same type. Look at total recur, the sum function from earlier. Its base case returns a number, 0. Its recursive step adds the first element to whatever the recursive call returns, and that addition only works because the call is guaranteed to return a number. Now look at in list. The length 1 base case returns a Boolean comparison. The early exit returns the Boolean true, and the recursive step returns whatever the recursive call returns. It simply passes the Boolean back up the chain of command. Numbers everywhere in one function. Booleans everywhere in the other. Break the guarantee. Say your base case returns a list while the recursive step tries to add numbers. And the moment Python reaches that base case, it complains that the types do not mix. Keep every return the same type, and each recursive step can build on the result without ever checking it. The arc of this video is the real workflow. The tempting first version recursed on the remainder without ever checking the element it dropped, so it silently tested only the last element of the list. A print statement inside the function exposed the skipped elements in 4 lines of output. The fix was a single comparison before the recursive call, and the cleanup collapsed the repeated branches into 3 clean cases. So write recursive functions the way you think, cases first, polish later, and keep every return the same type. That guarantees what the recursive step stands on. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.